Okay, welcome back. This is the fifth and final part of the lecture about transfer of heat through the Earth's atmosphere and radiation, which obviously has very clear implications for things like estimating the electrical yield and load. I mean, how much energy demand there's going to be, how much load there's going to be, as well as how much production of renewable power there's going to be by something like a solar panel. There's really only one topic left, and that's to talk about this business of the long-wave radiation part of the energy budget, and in particular to be talking about long-wave down. What determines the amount of long-wave down that the surface receives? Long-wave up is just determined by the emission of radiation by the surface of the Earth. That's principally depends on the temperature. Remember, that's Stefan Boltzmann's law. Stefan Boltzmann's law tells us that the amount of radiation being given off is principally determined by the temperature of the object. Well, what determines how much radiation is coming down from the sky at us? Well, this is the so-called greenhouse effect. The greenhouse effect is about the maintenance of the Earth's temperature through the action of greenhouse gases like carbon dioxide and methane and water vapor, as well as clouds and so on. All of these things are really good at absorbing long-wave radiation that is being emitted by the surface of the Earth and headed up towards the atmosphere. Those materials also are really good at emitting long-wave radiation. So, clouds are at a terrestrial temperature. They're going to be emitting long-wave radiation according to Wien's law. And some of that radiation is heading back down towards the surface of the Earth. We absorb it and we warm back up. So these materials absorb long-wave radiation and then emit long-wave radiation back towards the surface of the Earth in what is known as the greenhouse effect. That's actually a terrible name. Greenhouses don't work anyway like that. Greenhouses, the kind of glass houses that allow the temperatures to stay warm enough to keep your plants alive in the winter, they don't work anything about radiation or anything like that. They're about trapping a little bit of warm air near the surface using that glass house. But the intuition that this is sort of, it kind of keeps the Earth like a nice, warm, snuggly little greenhouse is, it was a good idea. And the more formal name for greenhouse effect in atmospheric sciences is actually the atmosphere effect, which is a terrible name. So greenhouse effect it is. I like the name greenhouse effect. And you know what? Without a greenhouse effect, the Earth would be much too cold to support life. Earth is too far from the sun to, if we didn't have an atmosphere, we would not be able to keep a greenhouse effect. We would not be able to keep the Earth warm enough to keep liquid water and so on. Any kind of life that we know about would not be possible on Earth without the greenhouse effect. It's a perfectly natural part of the Earth's atmosphere. Of course, the issue is, we are adding more greenhouse gases to the Earth's atmosphere every day, creating the so-called enhanced greenhouse effect. Now, we can talk about the enhanced greenhouse effect in great detail, but it isn't quite really what we're going to be doing in Energy 301. On the other hand, there's the new Environmental Sciences 105 course. It's a Magis Core course, Understanding Science course called The Science of Climate Change. That's what it is. I invite you all to take it, or encourage your friends to take it. It's taught by a great guy. Anyway, let's talk about the enhanced greenhouse effect just a little briefly, just kind of, because obviously that's going to be something anybody interested in environmental issues and power issues and emissions from fossil fuels issues and so on is going to be interested in. And so here's the deal. We know we add these greenhouse gases to the atmosphere by the gigatons per year. I mean, think about those train yards that go through Omaha, kind of parallel to Interstate 80. Every 5 minutes, a mile-long train comes through full of coal, headed off to the coal-fired power plants of the eastern United States. Just billions and billions of tons of coal gets burned each year, and it all ends up in the atmosphere in the form of carbon dioxide, as well as the burning of fossil fuels in cars and so on. Well, we know what these fossil fuels do, what these greenhouse gases do in the atmosphere. That's not a theory or something like that. We know the chemistry of that, as well as we understand the mechanics of how your cell phone work or any other physical process. We also know at the same time that the planet is getting warmer. We have lots of different kinds of observations from satellites, from weather stations, from monitoring of glaciers and so on. We know that every year the planet is getting warmer. We're clearly in some kind of change on the global scale of climate. We know that sea ice is melting. We know that every year the sea ice extent, okay, yes, obviously some years is a little more and some years is a little less, but superimposed on that, there's this very serious downward trend in the total amount of sea ice on the Earth. That's a very serious problem for climate. Sea ice has a really important role in climate systems. It separates the relatively warm ocean from the very bitterly cold air above it. think of like over Antarctica or something like that, you know, on some Antarctic ice sheet. The air above the ice might be negative 80 degrees Celsius, but the negative 80 degrees Fahrenheit, and the water temperature is obviously roughly 0 degrees Celsius, because 32 degrees Fahrenheit, because it's not frozen, and it's separated by sea ice. If you melt the ice, you can get a very different set of heat fluxes as heat conducts from the relatively warm, the scalding hot ocean from the point of view of the atmosphere, up into the very cold air above it. It has very big implications for ocean currents and so on. So we know that we are doing things that add gases to the atmosphere that could be causing climate change. And we know that the climate is changing. Is that proof? Strictly speaking, from the point of view of like the philosophy of science and so on, no, that is not proof. The truth of the matter is there could be natural processes that cancel out the impacts of what humans are doing, and then the climate change could be due to other processes. I mean, it certainly is the case that climate changes for natural reasons. Most of those climate changes aren't particularly fast, but some of them are fast, the way the kind of climate change we're seeing right now is. But see, science works. And what we know is we know the basic physics of how atmospheres work. We can simulate the atmosphere using computer models. Oh, hey, I tied this back to the modeling aspect of this module in the course. And these models can make predictions as to how much the planet should be warming based on how much greenhouse gases we have. And these models say that since the beginning of the Industrial Revolution, we have added a certain amount of gigatons of greenhouse gases to the Earth's atmosphere, and the planet should have warmed a certain amount. And then we know how much the planet has warmed during that period of time, and guess what? The numbers match. That is an amazing coincidence. Or, that's science. Kind of hard to tell, right? I mean, if the models had said that the planet should have warmed 20 degrees Fahrenheit in the last 150 years, and it's warmed like 1.5 degrees, we'd say something's very wrong. If the models had said the planet should have warmed 1/1,000,000 of a degree in that period of time, based on our greenhouse gases, and the planet had warmed 1.5 degrees, we'd know something was wrong. Clearly our ideas weren't very right. On the other hand, the models predict almost exactly what is observed. That's science. Is it proof? Strictly speaking, no. Strictly speaking, scientists could be making mistakes that cancel out. Maybe scientists do not understand the physics of greenhouse gases as well as we think, and it's just some kind of huge coincidence that like the crappy prediction we're making as to how much the climate should have changed just happens to match how much the planet changed. Scientists don't tend to believe in coincidences like that, but we're afraid of them. And so, strictly speaking, the fact that our models match what the world is doing is not quite exactly proof. But it is a smoking gun. The likelihood that the physics that our understanding of the physics is fundamentally wrong is very small. We do things about the physics of the atmosphere all the time, from making weather forecasts to understanding the data that we receive from satellites in orbit and so on. The likelihood that we are fundamentally misunderstanding how the atmosphere works in terms of like radiation moving through the atmosphere is just not very, very large. Science works. Perhaps more to the point, this is the best answer we're going to get. I mean, if you're talking about issues of global warming and so on associated with human activity, these models are the best answer we're going to get. Anybody who's waiting for a better type of science that's going to somehow explain how the atmosphere is changing is just going to be out of luck. This is the best we can do. All right, so again, I invite you to take Environmental Sciences 105 and encourage your friends and family members to do so too. I think it's a really interesting overview of what is the state of knowledge about climate change and so on. Here we were just talking about it in the context of radiative transfer and ways of moving heat through the Earth's atmosphere. So we've seen a whole lot of different ideas in this lecture. I recognize this lecture is longer than the other little pieces that we have in this module, but that's okay. I'll invite you to look through here and see if you have any questions about the topics that we have examined in this lecture, and we'll move on. I think the next one is pressure, if I'm not mistaken. Okay, please let me know if you have any questions. This has been Dr. John Schrage.